Today we're talking about section 7.5, complex fractions. So a complex fraction is an expression containing one or more fractions in the numerator, denominator, or both. An example you see would be shown below. 1 over a times b divided by 2 over b, and 1 plus 3 divided by 4 minus 6 over 1/2 plus 3 are complex fractions. Two methods will be presented to simplify complex fractions. The first method, that we call method 1, follows the order of operation to simplify the numerator and denominator separately before dividing. The process is summarized as follows. Now let's put stuff to the side. But this process is basically what we've been doing when we were getting common denominators between two or more fractions for last week. I don't know which section. Maybe it might have been like 7.4. I don't remember. Okay. So again, here's our steps, our little algorithm that we're going to use. We're going to add or subtract expressions in the numerator to form a single fraction. You know what? I've said before, this is a pretty good guideline to follow. But again, for the most part, it is, again, making a sandwich. You don't follow a particular algorithm to make a sandwich, right? You just know what you have to do. So we're gonna, I'll keep it here, but I will talk about this example the best way I can and put it in our language, right? Okay, so in order to simplify this fraction, we have to get a common denominator in both. Well, actually, no, we don't. There's an easier one. So they're starting out pretty easy here. So let's again reiterate that a problem like this, okay, is my students that have taken many math courses in college, because summer break, Christmas break, all that good stuff, right? If they see this particular problem, they freak out. They're like, "Oh, this is definitely not happening. Nope, it's a fraction over fraction. I don't play that game." All right. But if we remember that this is just 1 over. Let's try this again. 1 over. There we go. AB divided by 2 over B. Okay. Then of course we remember now that, oh, okay, so this is just 1 over AB times B over 2. Okay, that's it, right? And of course we do the multiplying here. And so this is just going to be B over 2AB. And then we know that the B's, okay, because they're factors, because they're being multiplied, I can cancel them, right? But let's say, for instance, it was 2A plus B. Okay, if it was 2A plus B, then we couldn't cancel because they're not factors. They're not being multiplied by one another, right? Well, because this B is by itself, but this B down here is being added. Okay, so we would not be able to just simply cancel those out. All right, but we do instead have B as a factor in the denominator, so we can proceed with our favorite method in mathematics, where we just cancel things out and never think about them again. All right, these A's, that's as good as it's going to get right now. All right, so that's example 1. Again, we take something that looks abundantly complicated, but then we can reduce it down into something that is a lot easier to play with if we just change it into a form that we're used to. Okay. This is where we have a little bit of fun. Okay, so in order to do what we did on the previous page, okay, because again, we can just simply take this and say 1, what's going on here? 1, there we go. plus 3 over 4 minus 1 over 6 divided by 1/2 plus 1/3. Okay, and it should probably look something like this. That way it doesn't look like it's just the 1/2 and 1/6 being divided, right? Okay, so if we have something like this, well, we can't really do anything with this, okay? So instead, we have to get a singular fraction. Excuse me. Instead, we're going to have to get a singular fraction in both the numerator and the denominator. Okay, so let us work on each of these terms individually. And honestly, if I say terms, I probably should have done this. Let us work on each of these terms individually. Okay, so what we need to do is get a least common denominator for my numerator and a least common denominator for my denominator. All right, so let's actually rewrite this particular problem, keep it in fraction form up here while doing that. Okay, so what is my least common denominator for my numerator? Okay, so looking at the first term, first term is going to be okay. Like whatever we choose, first term is going to be, I'm fine with whatever, right? Because it's a 1 over 1. All right, well, between 4 and 6, what is the smallest number that both will go into? And that's 12. Okay, so what I'm going to do is I'm going to multiply the numerator, every term in the numerator, by something to get the denominator to turn into 12. So 1, okay, how do I get a denominator of 12 with 1? Well, I'm going to multiply it by 12 over 12, okay, and then plus 3/4. What do I need to multiply 3/4 by to get a denominator of 12, right? So this 4 needs to be multiplied by 3, okay? So what I'm going to do is I'm going to multiply it by 3 over 3. And again, this is what we did last week. I am multiplying this fraction by different numbers, right? But I'm really just multiplying by 1, and that's completely okay. You can multiply anything you want by 1. It's a cool little manipulation trick to get things to look the way you want them to. Minus 1/6. All right. And how do I get a denominator of 12 here? Well, I need to multiply by 2. So we'll do 2 over 2. Okay. Now let's look at the denominator. All right, well, looking at the denominator, what do I need to multiply by to get what is my least common denominator? Well, that would be 6. So I need to get each term in the denominator to have a denominator of 6. So 1/2 times what will give me 6? Well, looks like it immediately be a 3, so just simply 3 over 3. And plus 1/3. And what do I need to multiply this 3 by down here? Well, that's a 2. All right, and now we can proceed. Okay, so 1 times 12 over 12, well, that's going to be 12 over 12, plus 9 over 12 minus 2 over 12. And then that's going to be all over 3 over 6 plus 2 over 6. 6 plus 2 over 6, okay? And again, the whole point of this was to get that common denominator in my numerator and the common denominator in my denominator. So 12 plus 9 is 21. 21 minus 2 is 19. So my numerator is 19 over 12. My denominator would be 5 over 6. Okay. And now we can write this in a way that we're familiar with, right? We can say, well, that's 19 over 12 is divided by 5 over 6. And that is the same thing as saying 19 over 12 times 6 over 5, which is equal to, let's do a cancellation real quick and make the multiplication a little bit easier. That turns into a 1, this turns into a 2, so 19 over 10, right? Okay, and that's it. Oh, I say that's it. I know. There was a lot in this, and as you see, this is called method 1. I'm not a particular fan of method 1. I do use method 2 that we'll see, probably maybe an example, starting example 4. Okay, let's do another example of method 1. Okay, so instead of numbers, we're going to have a bunch of letters. We love letters. I love letters. All right, so anyways. So again, we need to get a common denominator in my numerator and a common denominator in my denominator. Okay, so looking here, what would my common denominator be? Well, it was just going to be a combination there, right? X, Y, right? So what I'm going to do is I'm going to rewrite this, and I'm going to have to get a denominator of x, y. So this first term, 1 over x, okay, what do I need to multiply 1 over x by to get a denominator of y? Well, it's going to be y over y. Plus 1 over y. And in order to get that denominator of xy, I need to multiply x over x. Okay. And my denominator, let's look at my denominator. What's my common denominator here? Well, that's cool. This is going to be easy peasy. It's this x. Okay. So we're going to write, all right, how do I write x with a denominator of x? Okay, well, you would think, okay, well, it's already got a denominator of x. Well, it doesn't, right? Because x by itself is x over 1, right? So let's go ahead and write that. So x over 1 all right, and in order to get that denominator of x, we need to multiply by x over x. Okay, and one moment, let me shut my door. Oh, all right, excuse me. So, where was I? All right, so the second term on the bottom, so it's a y squared over x. So it's right, y squared over x. Okay. And how do I get that denominator of x? Well, I actually don't have to do anything to it, right? I don't need to multiply by anything to get the denominator of x because it's already an x. So I can now proceed. We're gonna multiply these. Put it in blue usually, don't we? Okay. So we're gonna put y over xy plus x over xy divided by x squared over x, and I'm going to have to open my door again. My cat just don't know what he wants to do. Minus y squared over x. All right, one moment again. Okay, so my numerator, I've got that common denominator. That was why I multiplied by what I did, right? So this becomes xy over xy. That's pretty. No, this becomes x plus or y plus x. Sorry. So go ahead of myself. Y plus x over xy and x squared x squared minus y squared over x. Okay, so I said ooh because whenever you see a difference of squares, we're probably going to have to be factoring, right? So let's go ahead and write this in our division that we're used to. So let's do y plus x over xy divided by x squared minus y squared divided by x. Okay, and again, you don't necessarily have to write this step, I guess, but I do it just to be abundantly clear, right? You could just jump straight to, staring at this. You could jump straight to just saying, okay, well, that's y plus x over xy times, and then I flip this denominator. So it'd be x over x squared minus y squared. Okay. Now before we proceed, let's actually go ahead and factor this, right? X squared minus y squared, we know factors into, because it's a difference of squares, factors into x plus y and x minus y. Okay. Let's fix this up a little bit. What was that? X? Okay. Okay, so here we can do some cancellations. So this x is going to cancel with this x, right? This x plus y is going to cancel with this y plus x, okay? Well, excuse me. The reason why is because addition is commutative, right? 3 plus 4 is 7, 4 plus 3 is 7. So I could really have rewritten this as x plus 7 for it to look the exact same, x plus y, for it to look like this, which is x plus y. But I do know that y plus x is the same thing as x plus y, so that's why I'm able to cancel that. And I think that's all I can do there. And there's only one thing that is left all alone. Well, two things actually. All right, so my numerator, I have everything in my numerators here, when I just multiply, have been canceled, right? But there still is a numerator there, right? These turn into technically ones, right? So when they cancel, they don't technically go away, they just become a 1. So my numerator here is a 1. And my denominator, well, it would just be y and then x minus y. And looks good. Whew, it's a lot of x's and y's, yeah? All right, so let's see if we jump to method 2 now, because I definitely 100% prefer method 2. Okay, good. So we're going to talk about method 2 now. Okay, so simplifying complex fractions, method 2. We will now simplify the expressions from example 2 and 3. So we're going to use the exact same examples, using a second method to simplify complex fractions. Recall that multiplying the numerator and denominator of a rational expression by the same quantity does not change the value of the expression because they're multiplying by 1. Alright, so this is basically saying what we're going to be doing here is, instead of multiplying each individual term by some number to get a common denominator in my numerator and denominator, right? And this example, we multiplied everything, every individual term by something to change the value, right? Instead, what we're going to do is multiply the entire fraction. So, example 4. That's not good. That'll do. All right, so what we're going to do is we're going to say, okay, so we're going to multiply my numerator and denominator by a common denominator all around, okay? So what I'm going to do now is I'm going to look at the fraction, the denominators of every single term. So obviously this is going to be a 1, this is a 4, this is a 6, this is a 2, and this is a 3. Okay, so let's just write this out. 1, 4, 6, 2, 3. What is the smallest number that all 5 of those will go into? Okay, well, it would be 12, right? They all go into 12, and that is indeed the smallest number that they go into. If you forgot how to do this particular procedure, you can go back and in my previous videos figuring out least common denominators, right? It does indeed involve making a prime factorization tree. But this one is pretty easy, 1, 4, 6, 2, 3. And the thing is, I don't think they're going to be abundantly difficult because, I mean, nobody wants to sit there and find the least common denominator of 5 terms, much less 5 terms who have a least common denominator of something like 311. Is that a prime number? Probably wouldn't. Well, let's say 312. Okay. All right. So anyways, let's write this fraction out. So 1 plus 3/4. Let's 3/4 minus 1/6. And again, this is just the same problem we did just a few moments ago. Threes are always a pain when I write them small. There we go. All right. So I said 12 was my least common denominator here, right? So I'm going to multiply this entire fraction by 12 over 12. Okay. And again, 12 over 12, that's just 1. I'm multiplying by 1, so I'm not changing the value of anything. Similar to the first 3 examples, except this time I'm just going to take care of everything all at once. All right. Now I said I prefer method 2, and in my opinion, it is superior, but you also have to get the least common denominator of every single possible term, numerator and denominator, as opposed to a least common denominator in just the numerator and a least common denominator in just the denominator. I don't know. You choose. It's either way you want to work it, but it works out the same both. Okay. So think about this as 12. Let's do this. We're just looking at my numerator. Think about it as 12 times the quantity of 1 plus 3/4 minus 1/6. Okay, and of course you would distribute, right? So that's what we're going to do. So we would just distribute and then distribute the same on the numerator. Okay, so let's start. So 12 times 1, let's see, it's 12. Okay, plus. Okay, so you could do this one of a couple ways. You could, if we let's focus strictly on this. Okay, so let's say it's written like this: 12 times 3/4. Okay, you could think of it like this. You know, multiply the numerator there, and you would say 12, 24, 36. So you would say 36 over 4, which is equal to 9. Okay, that's fine. Or you can think of it like this. Well, this 4 essentially goes away, and that 12 becomes a 3, right? Because it's 12 over 4. And then, of course, 3 times 3 is 9. Okay, so those are 2 ways you can go about doing this. Just the multiplying of fractions, right? So what did we say? It was 9, so let's just go ahead and proceed there. Okay, and then minus 12 over 6, so it's going to be minus 2. Right? Okay, and then my denominator, distribute here, 12 times 1/2, well that's going to be 6. 12 times 1/3, that's 12 over 3, which is 4, plus 4. So this is actually the same as we had in the first example. So 12 plus 9 is 21, minus 2 is 19 over 10. Same thing, 19 over 10. So let's go back and look at the differences, right? This is the example we just got done doing. Again, if you want to do it this way, if it seems just more precise to you, if it comes easier to you, then go for it, right? But again, I prefer this. And notice how it's just a lot smaller, a lot smaller in work, okay? In terms of work, rather. Right, and this was the other example we did with just letters. or variables we should say, but yeah, letters. So again, let's write the problem out here. So we're going to have a, can't put a little serif on there when it's tiny, plus 1 over y over e over, that's better, x minus squared x. Okay. All right, so same thing as in example 4. In order to proceed with method 2, I need to look at each denominator. Okay, and this is an implied 1, right? X over 1, so that's doesn't really care there, or does it? And then here. Okay, so my least common denominator of all my denominators would be x times y. Okay, if you recall, it's not going to be x squared. Okay, because we look at the factors, and since they're just by themselves, they are essentially factored as a denominator. You look for the highest factor, right? And these x's, the highest degree of x we see, the highest degree we see is just simply 1. So it's going to be x times y. So I'm going to multiply this entire fraction by xy over xy. Okay, and then again proceed to distribute. Okay, so xy times 1 over x. Well, the x's will cancel, right? So it just becomes y plus, well, kind of the same procedure here. If I multiply here, okay, be xy times 1 over y. Let's see, let me go back. Okay, good. I couldn't remember if I put parentheses around the actual problem or not. But anyways, so xy over 1 over y, well, that becomes, xy over y, the y's cancel, so we just have x. The denominator, okay, well, it's not the worst thing in the world, but we don't have to, do any sort of canceling, so it becomes x squared y, and then my denominator, or I'm sorry, distributing here, looks like the x will cancel, so it's going to be y cubed. Y cubed. Okay, so this doesn't look like the first problem just yet, right? Instead, what we're going to do is we're going to have to, looking at this denominator here, right? What can I factor out here? Well, it looks like just a single y. Okay, so I'm going to factor out a y, and what remains, well, would be x squared minus y squared. Okay, x squared minus y squared. Well, we know that's a difference of squares, so let's go ahead and factor that, though. Okay, so we'll say x plus y, x minus y, and that's all under y plus x. And again, similar to what we talked about on the example 3, y plus x cancels with x plus y, and we end up having 1 in my numerator, and then y times x minus y, which was the solution to 1 over y times x minus y. Okay, and again, going back, I mean, to me, this is just a lot more stuff, a lot more work than this. Okay. Okay, and I believe, let me double check. I believe this is the last example we've got. Yeah, then we got practice problems. Okay, so 1 over k plus 1 minus 1, and then 1 over k plus 1 plus 1. All right, so this denominator should be pretty easy to see that we're going to be using, so we're going to just go ahead and write this like we've been doing. Damn, I can't get that, whatever. For the sake of these complex fractions, we'll just go and do this. So 1 over k plus 1 plus 1. Okay, so looking at my denominators here, well, I got a k plus 1, doesn't matter, and a k plus 1, and then doesn't matter, right? So the denominator here is going to be k plus 1. So I'm just going to go and proceed with method 2, because again, that is my preferred method. So k plus 1 over k plus 1. Okay. And then we do the distributing process. So we're going to multiply here. Well, it looks like the k plus 1s will cancel, right? So we're going to have simply a 1 there. Okay. And then I'm going to multiply this k plus 1 times a negative 1. So it's going to be a minus, okay, k plus 1. This is where I feel like a lot of you, many of you, might get turned. Okay. So real quick, let's actually highlight that. K plus 1 times negative 1. Okay. So it looks something like this. Times negative 1. All right. So we're used to, let's actually not do it that way. Not do it that way, because that'll end up giving me negative k minus 1, and that's where we will end up eventually when we distribute, right? But let's not deal with it right yet. Excuse me. Instead, we'll just talk about this minus sign. So when I'm distributing here, k plus 1, I distribute by that number there, right? Same thing I've been doing on previous pages and so forth, right? I distribute by the number, but I have to respect that sign, okay? In the previous examples, well, I think there was a subtraction in there, but we weren't multiplying it by a binomial, I don't think. We're just multiplying by a single number. But we have to respect that negative sign, so we say that's why I put the minus right here. Okay. Now again, and I don't suggest this at all, you could just go ahead and write this as negative k minus 1, but I feel like writing it like this is more precise, and you don't lose track of negative signs, which, let me tell you, you will. And I only say that because I do. All the time. Okay. Anyways, my denominator, right, I distribute here. Well, the k plus 1s cancel. So I'll have a 1. And then this is exactly what I'm talking about. I guess I could have just looked down for a hot second and I would have been able to explain this better. All right, so we're going to distribute by this 1, right? But we have to respect that sign. And so we're going to put a plus, and we're still going to put this in parentheses, okay? Because we're talking about a binomial here, because there's going to have to be a distributing process here over the binomial, which it is just going to be k plus 1. But the previous example we did, let's go back. Okay, this would be an example here. So when I distribute this 12 over here, right, it was 12 times 1/6 times 1/6, which is a 2, right? But then we have to respect that sign there. Okay, so that's why we put that minus 2 there. So that's the thought process. Hopefully that's not too confusing. Maybe I just said too much and got a little more confusing than I already did. But I do know that negative signs is an issue because, well, it's always been an issue, right? It's just the way it's going to be. But anyways, we can rewrite this as, looks like 1, and then it's going to be, we're going to distribute the negative through. Okay, so it's going to be a minus k minus 1. Minus k minus 1. And then my denominator is going to be a 1 plus k plus 1. Put the little flag on there. Okay, there we go. All right, well, now it looks like, we'll just put an equal sign down here. Okay, so we can combine like terms here. Okay, so we have a positive 1 minus 1. Okay, well, that's just going to be a 0, right? So we can those are going to cancel off next to the numerator. So what remains is a negative k, and my denominator, my two 1s are going to be combining. So I've got a k plus 2. Okay, and there's nothing more I can do with this, and that is the end of this particular problem. And that also concludes today's lecture.